Hi everyone. The last thing I want to work on with this whole derivative is a function business. Is just being able to look at the graph of a function and get a pretty good idea of what the graph of its derivative looks like. So, let me try to move. I did. I don't want my pen to bleed through. Okay, so I'm going to walk through this first one, and then my advice would be whenever you're comfortable, try and pause and sketch the derivative yourself, and then come back and check in. So just so that you have good ideas, I'll work on this first one, but I recommend doing that for all of the rest. In class, I would definitely have people be trying this, and I'd go around and check on them. Okay, so this is my function. And what you want to remember is that the derivative, which we're supposed to sketch below, will have the exact same x values, but its y values should be the slopes from this function up above. So my favorite thing to start with is usually the flat spots, because those are really definite. The rest of it's kind of all estimating, but I can get a pretty solid idea of where I have flat spots. And at a flat spot, at a little peak or valley, your tangent line is horizontal, which means your slope is 0. So right here, my y value should be 0. And right here, my y value should be 0. So there are the x-intercepts of the derivative. Okay, so the rest of this, I think you just want to try and talk yourself through what the slopes are doing. So you can even picture a line here. So I would say my slopes are big positive, and then they get smaller and smaller and smaller until I hit the flat spot. And then my slopes become negative and they get steeper for a little bit, and then they start to get less steep until I hit the next flat spot. So those are negative, more negative, less negative. And then out at this end, they become positive again, and they just get bigger and bigger and bigger as my x value increases. So now you want to reproduce that as, restate that basically as y values. So I have big positive y values, but they're getting smaller, and then they become 0. And this is just really approximate for this. Don't worry about being too perfect. There is kind of a grid here, but I haven't told you a scale, and that's deliberate. So big positive, smaller, 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 0. That's going to look like big positive, smaller, 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 0. And do zeros have to look exactly like mine? No, but it should be starting up a little higher and then decreasing to 0. That for sure should happen. On the right hand side of the little flat spot, I said I have small negative and then bigger negative and then back to smaller negative slopes. So here my y value should get a little bit negative and a little bit more negative and then a little bit less negative and then back to 0. On the other side of this flat spot, their slopes have returned to positive. So small positive, bigger positive, bigger positive. You can draw those tangent lines in, and that's what you want to reproduce with your y values. Small positive, bigger positive, bigger positive. So there's a rough sketch of the derivative, and that really is all I'm looking for in these, is just for you to get that rough sketch shape. So if you're feeling good about it, pause and try as many of these as you feel comfortable with, and then just come back and check in if you get stuck or if you want to see if your picture is right. The second one is actually a slightly funny one. It looks to me like I have asymptotic behavior, which generally any sort of asymptotic behavior on the function will lead to some sort of asymptotic behavior on the derivative. So I don't have the nice flat spots to start off with. What I see is that I start with somewhat negative slopes, and then they're getting less and less and less negative and approaching 0. So I need to start with some kind of medium-sized negative number, and then my negative numbers, my negative slopes, which become my y values, are getting closer and closer and closer to 0. So these are going to approach, y values are going to approach 0. So it sort of just looks like a reflection of what we started with. It might not be stretched, it might be a lot flatter or a little steeper or something, but that one, you'll see that horizontal asymptote actually carry through to the new one. do think carefully about that. Even if this asymptote wasn't at 0, this one would be. The reason this asymptote is at 0 is because when you have a horizontal asymptote, your slopes approach 0. Okay, next one. I have lots of flat spots to work with. So I see flat spots here, and here, and here, and here, and here, and here. Okay, so that's, if the slope is 0 on the function, the y value will be 0 on the derivative. So 0, 0, 0, 0, 0, 0. Okay, so the x-intercepts of the derivatives match up with the flat spots on the function. And then in between, I see, here I'm going to pick some colors to show this. I see negative slopes on some of these intervals, and I see positive slopes on the other one. So we have this alternating positive slope, negative slope thing happening. So I see here I'm starting with a negative slope, and then it's getting closer and closer to 0. So it's flattening out. So I'm going to start negative, get closer and closer to 0. And then they switch to positive, and they get a little bigger and then come back to 0. And I see some symmetry happening. If we draw a line right here, these two seem symmetric. So however far below I think this went, this should go up pretty much exactly that far. So we shouldn't have these going way up above and not very far below, because these steepest points all appear to have some pretty solid symmetry going. So slopes get a little bit bigger. They're the biggest right here in the middle, and then they start shrinking again. And then they get negative, and they get a little more negative, and then they start getting less negative. And then they get positive and a little more positive, and then back down to 0. And we pretty much just keep repeating this. So this is another one that looks sort of similar to the function I started with. Not exactly the same, but there's definitely similarity there. And how high these go up, we don't know. So I'm just kind of approximating here. Yours could go up higher, or they could be even flatter. What's important is that the tops should all be consistent and the bottoms should be consistent, and they should be equal distance from the x-axis because of this symmetry. Okay, so something along those lines for P. For Q, I see asymptotic behavior again, which is always interesting. So I do have flat spots, 2 of them. So I know that right here I have a 0, and then right here I have a 0. Okay, and I see negative slopes, starting off pretty small, and then they get a little steeper, and then they get a little less steep. And out here I have negative slopes, and then in the middle I have positive slopes. Okay, so my y values should start off really close to 0, but a tiny bit negative. So negative, but really close to 0. They should get more negative for a little while, and then at some point they start to get less negative. So I would say that's right around here. So these guys get more negative, and then less negative, and then 0. And then they switch to positive, and they get a little bit positive, a little bit more positive. I would say it's steepest right around the origin. And then they start to shrink back down to 0. Again, I have some really nice symmetry here, so I should have some sort of symmetry happening down below as well. Okay, and then last stretch, they get a little bit negative. I would say they're steepest somewhere around there. They start getting less negative and approach 0. Okay, so a little bit negative, a little less negative, and then approach 0. So that's a rough sketch of that derivative. Okay, and then on the last page, there are 2 more. And then you definitely have more on your homework to check yourself with. All right, so this one, I see 1, 2 flat spots. So I'm going to carry that down to 2 x-intercepts. And then I see everywhere else positive slopes. So this is fairly big positive, and then it shrinks, and then it's 0. So I'm going to start fairly big positive, and then it's shrinking down to 0. But then I'm not going to cross through because they become small positive again. So this is like bouncing off somehow. And then they get bigger and bigger and bigger. It looks to me like at 0 is about the biggest. And then they start getting smaller again, not negative, but less positive until I hit the next flat spot. And then once again, the slopes don't become negative, they just switch to positive, and they get bigger and bigger and bigger. So something along those lines would be my picture. Okay, and then last one here is actually fairly simple, but it has the corner. I wanted to make sure that we saw at least some funny stuff with not being differentiable. So we know that sharp corners are bad news, that the function, the derivative should be undefined whenever the function has a sharp corner. So let's look at the two pieces. This is coming in, it's linear, so it has a constant negative slope, which means on this picture, I want to see constant negative y values. And I don't know what the y value is, but just it should be coming along, all staying the same and being negative. And then when we get to the corner, it abruptly becomes undefined. So I'm going to end that with an open circle. On the other side, I have, it looks like the positive version of the exact same slope. So I'm going to say, okay, well then maybe this is right around here. And again, I don't know what the y value should be. I just know they should be opposites. Whatever this is, this should be equally far above the axis. And then same thing here, the derivative is undefined. So that's actually what the derivative of an absolute value looks like. Okay, thanks for watching. So definitely give those a try on your homework and let me know if you have any confusion about how to get that.